All right, just gonna make a quick video going over the Classkick problems that are gonna be useful for the test. So let's just get right to it. Here we got a 10 kilogram ball moving 3 meters per second to the right. So let's draw a picture to kind of understand what's going on. So we got 10 kilograms moving 3 meters per second, and it's gonna hit a wall. All right, the ball's then gonna bounce off of the wall at the same speed, right? So now it's going to be going to the left. All right, and it's saying, what is the change in momentum? So you're going to have access to all the equations on the equation sheet, and I'll also put them up on the board. Basically we know that the change in momentum is equal to the final momentum minus the initial momentum. And the definition of momentum is mass times velocity. So here we have an initial momentum equal to 10 kilograms times 3 meters per second, and you get 30 kilogram meter per second. One thing that's very important about momentum is that it's a vector, so you have to consider if it's going in one direction, say going to the right, we're going to consider that to be positive, and going to the left, that's going to be considered negative. So it's very important when you do the problems that if they're going in different directions that they have opposite signs. So here I have positive 30 kilogram meter per second. For the final momentum, I have, again, it's the same ball, 10 kilograms, except now it's going 3 meters per second to the left. So that's going to mean it has a velocity of negative 3 meters per second, right? So think of it kind of like the number line, right? The numbers that are going to the right, those are positive. Numbers going to the left are going to be negative. So here we have a final momentum of negative 30 kilogram meter per second. So if my final momentum is negative 30 and my initial momentum is 30, right, I have negative 30 minus 30, and I get negative 60. So negative 60 kilogram meter per second. Alrighty, so next one. Here we have a 4,000 kilogram train car moving at 2.5 meters per second. It collides and couples with a 1,000 kilogram train car at rest. So that just means that they're going to stick together, right? So when reading this problem, you understand that they're going to stick together, and we're dealing with a collision. Specifically, it's an inelastic collision. Okay, so for an inelastic collision, let me draw it out first so we can understand how it works within the equation. So we have here the 4,000 kilogram cart moving with a velocity of 2.5 meters per second. It's going to combine with a 1,000 kilogram cart with a velocity of 0, right? And the reason we know the velocity is 0 is because it says that it's at rest. All right. After they collide, they couple together, and it's as if it acts like one large object. Okay, so they're going to have some final velocity. And we know that the final velocity for both has to be the same because they're physically connected at that point. They're moving together. So if I write out the conservation of momentum, right? So momentum is conserved in all collisions. We know that if there's no net external force, right? So in this case, we're looking at the whole system. The initial momentum of the system is going to equal the final momentum of the system. And this is just like the lab that we did with the carts that had the Velcro on them when we measured the velocity going in and the velocity going out. So here we have M1 V1 naught. So what this means, just to clarify, this is velocity of object 1, and the naught to the little 0 there, that's at time t equals 0, right? So at the very beginning of the motion, how we're measuring the motion of the train car, it starts at 2.5. For the second object, the 1,000 kilogram train car, its velocity is going to be 0, right? And that's the total momentum of the system before the collision. The conservation of momentum tells us, well, it has to be conserved if there's no net external force. So I know this has to equal the final momentum, but the way I'm going to express that is that I add both masses together and I multiply them by the same final velocity. So it's like it acts like a large train car system of 5,000 kilograms moving together. So at this point, you're going to want to just plug in the values. We understand that this is going to be 0, right? Because anything times 0 is 0. So the second train car is at rest. It has 0 momentum. And I have 4,000 kilograms times 2.5 meters per second. That has to equal 4,000 plus 1,000. I should put the units as well. Kilograms. Okay. Times the final velocity. We're not sure what that is. And we have to calculate it, right? So just go through the algebra. We know this comes out to 10,000 kilogram meter per second. That's the initial momentum of the system. And that has to equal the final momentum, which is 5,000 kilograms times whatever the final velocity is. And at this point, we divide both sides by 5,000 kilos, and we get a final velocity equal to 2 meters per second. So we get 2 meters per second. All right. And that is the answer to that one. For the third one, here we have, all right, so it's very helpful to kind of draw a picture. These problems are a little short in terms of how they describe in the situation, simply because I pulled these from an older Kahoot, and you're kind of limited on how many words you can put into the questions on Kahoot. But basically what this is trying to say is that both of the carts, they're at rest. There's a spring between them, right? So V1 naught is 0, V2 naught is 0. The entire momentum of the system is 0, right? So when the spring is released and it's able to push on both carts, right, I know that the total momentum has to be still 0. But the idea is that they're going to have equal and opposite momenta, right? So now this cart on the left, the 1 kilogram cart, is going to be moving to the left, and the 2 kilogram cart is going to be moving to the right. We know that the velocity of the 2 kilogram cart is 3 meters per second, right? So that results in a momentum of this cart of -6 kilogram meter per second, right? Because we know that the momentum is just m2 times v2f. All right, so basically, the easy way to think about this problem is I know whatever the momentum of the first cart is, it has to add to -6, and the total has to be 0, right? Because of the conservation of momentum. If you want to write it out in terms of the variables, let's be thorough about this. So you have m2 v2 naught. That has to equal m1 v1f, right? So that's the final velocity, v2f. So that's what we're trying to solve for, the final velocity of cart 1. This is going to be 0. This is also 0. And just plug in the values here. I have 1 kilogram times v1f, which is what we're solving for, plus 2 kilograms times what's it called? 3 meters per second. Right, so we calculated here, that comes out to -6. Wait, whoops, I am kind of jumping the gun here. So we're going to call going to the right positive. That's the standard, all right? I'm kind of immediately going to the answer, but it's +6 kilogram meter per second. All right, so we have +6 kilogram meter per second. Okay, and when we're solving for this, I'm just going to move the 6 to the other side of the equation, right? So 1 kilogram times v1f plus 6 kilogram meter per second has to equal 0. So then I have -6 kilogram meter per second equals 1 kilogram times v1f. All right, and then obviously I'm just multiplying it by 1. So, you divide both sides by 1 kilogram, and you end up with a v1f equal to -6 meters per second. So again, to clarify, the initial momentum, going over the entire problem, the initial momentum of the system is 0. Therefore, the final momentum has to be 0 because there's no external forces. That spring in between the carts, that's considered an internal force, right? Because we're looking at the entire system. Let me see if can I change colors on this. Yeah. So we're looking at the entire system, right? So the cart spring system, right? And actually, I want to talk a little bit about systems just to clarify. So if you look at the individual momenta, right? So if we only look at the 1 kilogram cart, it starts at rest and then it's going to be moving to the left, right? So if you zoom in and you only look at the 1 kilogram cart, yeah, its momentum is going to change, right? Because in that case, if you're zooming in, you're not even looking at the whole system. You see that the spring applies a force to the left on the cart, and that's what causes it to accelerate to the left and attain some final velocity going to the left. And then the 2 kilogram cart is going to experience an equal and opposite force, right? So if you zoom in on the 2 kilogram cart, you know that starts at rest. The spring would then be considered an external force, and that's why it gains some momentum. But if you look at the big picture, right, if you look at the entire system, the initial momentum of the system is 0, and the final momentum of the system is 0. So basically, the way that works out is afterwards, the 2 kilogram cart and the 1 kilogram cart, they're going to have equal and opposite momenta, right? So the answer to this is -6 meters per second. And meanwhile, I'll change the colors. So here, I have a 2 kilogram cart initially at rest, has a fan that applies a 3 Newton force for 4 seconds. What is the final velocity of the cart? So for this one, if you're seeing force and time in a problem, you know that you're dealing with impulse, right? And the equation we're going to use is the impulse momentum theorem, right? So what this says is that if there is an external force, right, the amount by which the object's momentum is going to change is going to equal the average force acting on that object times the amount of time that's in contact, right? So in its equation form, the change of momentum is equal to force times time, all right? So here, the change of momentum, we know it's initially at rest, right? So if I know that change of momentum is P final minus P initial, right? And the initial momentum is going to be 0 because it's at rest. Okay, so I'm just basically just looking at the final momentum of the system, right? So M1 V1F. So I don't even have to put M1. There's no second object, right? So just MVF. So MVF. And the cart applies a 3 Newton force for 4 seconds, right? So MVF is equal to 3 Newtons being applied over a time period of 4 seconds. All right, and we know the mass of the cart is 2, right? So 2 kilograms times VF has to equal 3 times 4, right? So 3 Newtons times 4 seconds, that's an impulse of 12 Newton seconds. And a Newton second is the same thing as a kilogram meter per second. So a Newton second is the same thing as a kilogram meter per second, right? If you look at the SI base units for newtons, right? Newtons comes from Newton's second law, right? We have a mass times acceleration, that's kilogram meter per second squared. And if I multiply that by seconds, I get kilogram meter per second, right? So those units are equivalent. It's just that when you're talking about impulse, you typically write it as Newton times seconds. So don't fixate so much on the actual units, all right? Just understand how to actually set up the problem. So we know here that the final velocity, I'm going to divide both sides of the equation by 2 kilograms. So 12 Newton seconds divided by 2 kilograms. As long as you have the final unit correct, right, we know that velocities are measured in meters per second. So we have 6 meters per second. All right, 6 meters per second. And then finally, the last problem. So another 4,000 kilogram train car is moving at 2.5 meters per second. So moving at 2.5 meters per second. And the engineer applies a force. The braking force is a constant 2,000 newtons. How long does it take the train to stop? So again, we're doing the same thing. Change momentum is equal to force times time. All right. Now in this case, the final momentum is going to be equal to 0. All right. So if I think about what's going on here, that braking force, right, that's basically like a force of friction. Where it's going in the opposite direction of the motion of the object, right? So here we know that the change of momentum, again, just like the last problem, it's the final momentum minus the initial momentum, right? And it turns out the final momentum is going to be 0, right? Because when you stop, you're no longer moving, so your final momentum is going to be 0. Final velocity is 0. Your final momentum is going to be 0. So the change of momentum in this case is just the negative of the initial momentum, right? Then that's just going to equal m times v naught, or negative mv naught, I should say. So negative mv naught. And now let's write it out. So I have negative mv naught is equal to the braking force, right, which is 2,000 newtons. Now, I wouldn't fixate so much on the minus sign or the plus sign, but if we want to be thorough about this, you need to understand that the if it's moving at 2.5 meters per second, right, positive 2.5 meters per second, we know that the braking force has to go in the opposite direction, right, because that's what actually causes it to decelerate. So the force acting on the train car is going to be opposite of the motion of the train car. If it was in the same direction, it would be speeding up, but it's not doing that. It's slowing down. So mathematically, we have to say that it's a negative force, right? If we're going to call that velocity positive, then the force has to be negative because it's also a vector and it's pointing in the opposite direction. And that is applied for a certain amount of time. We don't know what the time period is, right? So delta t. And let's just do the math. So we got to solve for the time period. We're going to divide the momentum of the cart by the force, right? So let's just write this all out. So 4,000 kilograms times the velocity of the cart, which is 2.5 meters per second. And I'm going to divide that by negative 2,000 newtons. And that's going to equal the time period. And here I have, so 4,000 times 2.5, that's 10,000 kilogram meter per second. Divide that by 2,000. And I'm just ignoring the minus signs because you have a negative divided by negative is, well, that's just going to be a positive, right? So here we have 5 seconds. All right, so 5.0 seconds. All right, so that's pretty much it. Also, again, with significant figures, right? So let's make sure we put the right amount of significant figures in the responses. So here, all these have 2 sig figs. So 6.0. And I think everything, yeah. So technically this has 1 sig fig, but we get the idea. All right, yeah, that's also just 1 sig fig. So again, you can also go through these problems yourself, and to make sure you're getting it right, the little green box, it tells you what the answer is, right? And the whole point is just to make sure you know how to do the problems. So anyways, I'm going to just keep it short. If you have any questions, just let me know. I'm more than happy to help during Pride Block or right before you have to take the test, or if you just want to cover any sort of last minute questions, we can go over that. I want to make sure we do well. And that's pretty much it. So good luck when we take the test.